Well, this is a continuation from the last video, and we left off with this question where we had already determined that the harmonic series, or the sum from n equals 1 to infinity of 1 over n, diverged. So diverges, and we determined that the sum from n equals 1 to infinity of 1 over n to the 3/2, it converges. And we also used a little bit of logic, and we said, well, if we increase the exponent, of any 1 over n to that exponent, well then by increasing the exponent, we will decrease the sum of the series, which means that we will have a series that is smaller than a convergent series, which means that if our exponent, and we say our exponent is t, if our exponent was t, and t is greater than or equal to 3/2, well, by our intuition, we will know that it will converge. And that was by no means a rigorous proof, but it will be good for now. So it would also converge. And well, that's a lot of numbers. That's a lot of exponents that we've been able to determine the convergence of now. But we are still somewhere between the exponent of 1 and the exponent of 3/2, or 1.5. And we wanted to determine where, at some point within or on the endpoints of this interval, did the series begin to switch between being divergent, and convergent. And we also know that we call this genre of series, or the genre of associated integrals, we call them p-series, where p denotes, and I'm not really sure why I used t down here, I'll replace that with p, where our p will denote our exponent. So what we'll do is we're going to actually set up an integral. So we'll have the integral from 1 to infinity of 1 over x to the p dx. And we will solve this improper integral, and we will try to determine for what values of p does this integral and the associated series converge, and for what values of p does the associated series and integral diverge. So if we solve this, well, we can rewrite this as the integral from 1 to infinity of x to the minus p dx. And well, this will equal the exponent plus 1, and then we divide it by that. So we will have 1 over, well, that'll be 1 minus p, and then times x to the 1 minus p, and then from 1 to infinity. Well, now when we evaluate this, we will take the limit as b approaches infinity of 1 over 1 minus p times b to the 1 minus p, and then that will be minus 1 over 1 minus p times 1 to the 1 minus p. Well, on the right-hand side, 1 to the 1 to any power is just 1. So then we would have now the limit as b approaches infinity of 1 over 1 minus p times b to the 1 minus p, and then that would be minus 1 over 1 minus p. Okay, well, let's start off with just a couple of values. Let's say what happens when p is equal to 0, right? And I'm going to change colors one more time. Let's say what happens if p is equal to 0? Well, if p is equal to 0, then we would get the limit as b approaches infinity, right? So we'd get the limit as b approaches infinity of 1 over p, 1 minus p, times b to the 1 minus 0. So that would be b. And here the b would increase without bound, and this would diverge. So that would diverge. Okay. Now, what happens if we say, okay, well, p is equal to 1? Well, we already did that before, right? That was the harmonic series, and here it is, we can do it again, and we see, well, okay, we would get the limit as b approaches infinity. Well, we would get we would get b to the 0. That would be 1 over, but we would have a 1 minus a 1, and that would be 1 over 0. So this would also diverge. And they would also, since this would diverge, and since all values of p less than 1 would be larger than the integral for p equals 1, well, we would know that this would also diverge. So we would know that they would diverge for all values p is less than or equal to 1. Okay, well, let's look at values where p is greater than 1. So if p is greater than 1, well then what will happen is we will have the limit as b approaches infinity of 1 over 1 minus p. And note that if p is greater than 1, we will not be dividing by 0 in the first part. And then we will have b to the 1 minus a number larger than 1, which means that we will have a negative number. We will end up with some sort of negative number here. And I will say negative, and then I will do, actually I'll just do a hashtag, so negative number. Okay, which means that we can bring the b down to the denominator, right? So then we could rewrite this as the limit as b approaches infinity of 1 over 1 minus p times b to a positive number. Okay, and 1 over some number times our variable to a positive exponent, well, that will equal 0 because the denominator will increase without bound and the numerator will stay the same. So that means for all values p is greater than 1, our limit as b approaches infinity of 1 over 1 minus p times b to the 1 minus p, and then minus 1 over 1 minus p, well, this part will equal 0, which means, and I'll switch back, well, this will equal negative 1 over 1 minus p, which is really just equal to 1 over p minus 1. Okay, so we've basically shown now that there are two cases. Either our p is less than or equal to 1, and in that case, the series or the sum will diverge. And we've also shown that in the other case, p is greater than 1, well, it will converge. So very quickly, I'm going to put 3 examples on the board, and they'll be very quick examples. So n equals 1 to infinity. Let me write this 2 other times. N equals 1, infinity, integral n equals 1 to infinity. And if I had, okay, well, I'm going to have n to the second power, and this will be over n to the 3/2, and I will have right here, this will be n cubed over 4 n cubed, and then I will have, in the last one, I will have n squared over n to the 4th. Okay, well, if we simplify these, then we will get, okay, well, we will get a 2 minus a 3/2. So this would equal 4 over 2 minus 3/2, which would equal 1/2. So this would equal the sum from n equals 1 to infinity of n to the 1/2. And you would probably be quick to think, okay, well, here the p is equal to 1/2, right? And then you would start to determine the convergence or the divergence, but it's very important to remember. And then actually in this case it would work, but we would have to first put the denominator or the exponent into the denominator. So we would have n to the minus 1/2. And now we would say, okay, well, p is equal to minus 1/2. And since minus 1/2 is less than or equal to 1, well, we would know that this diverges. Okay, now in this next example, well, we would obviously have the case where the exponents cancel out, so this would equal 1 over 4, and we would have the case where it diverges. Here, our n would actually just be equal to 0, and since p is equal to 0 and it's less than or equal to 1, well, it would diverge. Well, in this case, we have n squared over into the fourth, which would equal 1 over n squared, and without even calculating the actual value of this sum, we would quickly identify that p is equal to 2, and since 2 is greater than or equal to 1, we would know that this sum and the associated integral, right? If we took the integral from 1 to infinity of 1 over x squared dx, well, that would also converge. Okay, hope you found the video helpful. I know the examples at the end weren't probably examples that you would normally see, but I hope they helped drill in the idea of the p-series. Very quick, easy way to identify whether a series converges or diverges. If you have any questions, please leave a comment below. I'll be sure to respond, and I will see you in the next video.